Welcome to Careless Coder. Today we will have a look at RabbitMQ or RabbitMQ in combination with Rust, making baby rabbits. Motherfucker! So RabbitMQ is a message bus. It allows you to send in messages, being a publisher, and consume the messages, being a consumer. And I have written a client server or consumer publisher about 6 years ago in Spring Boot, because the template version did not have all the functionality implemented that the DevOps team wanted, like naming the queues. TLS, for example, was not completely implemented or didn't work properly. So I had to revert to the documentation and actually build a class or a set of classes that allowed to be using all that functionality. So I actually know quite a lot about RabbitMQ, and I figured we're going to use this in Rust as well, so why not investigate this and write up a little consumer and publisher that survive server reboots, so we can build upon that. And I figured let's share that information with you in case you like it. So let's jump in and watch some rabbits in a queue. First, install RabbitMQ server. I'm using Pacman on Manjaro. Use whatever distro you have. Then you need to start the server with system control start RabbitMQ. And then we're going to install the RabbitMQ Manager plugin, which allows you to actually use the web manager. And that's RabbitMQ plugins enable RabbitMQ management. And then you can browse to your local host, port 15672, and there you go. Now first we're going to create an exchange, because queues bind to an exchange, and that binding process is called a channel. And since we're going to log system monitor events, let's call it system monitor. Now you have a direct, a fan out, headers and topic. We're going to fan out to a lot of different queues, and I keep it on durable so that it survives restarts. Now currently there are no bindings because we do not have a queue bound to it. Now for testing purposes, let's create a queue manually called listener1. And I created transient so that when the client disconnects or the server restarts, then the queue is gone. And here you have some properties that may sometimes be convenient. So add queue, and then we bind it to the exchange. That way, when a message is sent to this exchange, it will push it in that queue, or queues in this case, because it's a fan out, not a direct. We don't have a routing key. You can use routing keys to route a message to a specific queue if you also put a routing key on the queue, but we want this message in all queues. So now we see it's bound, and we can publish a message into that queue. So let's blah, very, very interesting message. And we see it's published. Now if we go over to the queue, we should see that there is one message pending. And yes, ready, one message, there you go, nice graphs, or as I call it, management porn. We see this queue is bound to this exchange. A queue can be bound to a lot of different exchanges, by the way. So now if you do a get, we can see the message, but it's still in the queue, because standard when you click on the get message in this interface, it is set to not acknowledge, so it stays in the queue. If you select automatic egg and you click on egg, it will actually acknowledge it and remove it from the queue. So this works. But since it's a fan out, let's create another queue called listener2, and let's create another one called client. Now these queues are normally created by the software. So our Rust consumer will actually create this client and binds it to the exchange. What we do manually now is done in code later on. So let's bind these to the exchange. So go to the monitor, system monitor, exchange, and just add client and listener2. So now we see we have several queues listed in this exchange. And if we now publish a message, what is appropriate? Fan me, baby. I think that is cool. Fan me, baby. Yeah. Publish. It is now published in all 3 queues, or it should, because that is what we configured. So let's check. Let's go to the queues. And yes, I see 11111. So we send one message and it's fanned out to all the queues, to all the subscribers. So you can already see the value. Now let's get this with an acknowledgement so it doesn't linger in the queue. So that is gone there. Yeah, let's do it for the other 2 as well. Acknowledge, baby. Yeah. And one more time for that last queue. Sometimes this updates only every 5 seconds, so you can force a refresh. That's why you still saw that one. Acknowledge, yeah. And that is nice and clean. So you see how easy it is to have a client create a queue, subscribe to a exchange, and then receives all these messages from this exchange. It's so much easier than having to code this in microservices yourself. To do that fan out, it's done automatically. So let's have a look at the code. Don't mind the squigglies. I did not install everything on this host. So first we start at main, then we work our way up into the different functions. And this is the publisher. So what this does is actually it will gather system information thanks to the great channel Faster Than Lime that actually did a nice little video on creating a web-based HTOP. And I figured, that is kind of cool for this demonstration. Just gather system resources. It changes quickly, so it's a good visual aid. So first we create our login credentials, RabbitMQ connect or Rabbit connect. Put in the host, it's a local host, the port number, the username that we use to consume. So this is the username consumer with the password Krebs. And well, this is for that system gathering. Then we create our connect Rabbit connection. And then we wait for that channel to bind. And then we go into this loop where we actually do the get sysinfo to collect all that information. And we await. So this will loop forever until it breaks. Then it gets here. And it will go into this reconnect loop because we will connect RabbitMQ also in this git sys connect. So let's go to that connect RabbitMQ. Where are we? Connect RabbitMQ, there. So these are the connection details that we pass in. And we open a connection with the open connection arguments new with the connections from our connection object. And we bind that to a virtual host. Now usually you will change your virtual host to / and your service name. So if you have, for example, a service account balance, then / account balance. That way you know to which services to send. And here we go into this error loop. So as long as there is an error, we're going to try to connect. So we sleep for 2 seconds. We try to open the connection and await it. If it fails with an error, we just connect again every 2 seconds. This is our reconnect loop. Then when we have a connection, we can actually unwrap it. We can do that safely because it only gets out of here when it actually is connected. And we register the standard callback, and this is the default callback, so that will always be there. We can safely unwrap that as well. And then we have our connection. That's what we pass back. That's what we saw here. Then we need to pass in that connection to create a channel. So we go to Rabbit channel RabbitMQ, channel RabbitMQ, here we go. And the channels should always be there because we created it ourselves, so we can unwrap it, but you can also basically just do the same loop like we did here in this channel as well. So we unwrap it and we return a channel. I don't know why I put return in there. There's no need. I can just do this, but hey. Right, so now we have a valid setup. So we have a connection, we have a channel, we have our connection details, and we have our sys and our details for that we can actually publish into this. So here we go into that get sysinfo. So these are the variables where we just saw. We will refresh our CPU, we will refresh the memory, and we set them in that details structure. Here we go through all the CPUs, set each CPU in that detail structure. And then we serialize it into JSON, and otherwise we send in an empty. And we call send with all the details, and we await that. Now the send is actually where we check if everything is in order. If not, we will call that reconnect. Hence we pass in the whole connection, channel, etc. So is the connection open? No, then we cannot send. Then we need to call that RabbitMQ connection again, where we just saw that it tries to bind to RabbitMQ. If that finally passes, because that you only get out of that await when it actually is successful, then we have a valid channel we can await. And like I said, you can also do that there, but since that is basically the channel that should be there, we can just assume it's unwrapped. And then we say, oh, we got a connection. Now the channel can break, of course. So if the channel is not there, we so if the channel is not there, we're going to connect that RabbitMQ channel. And otherwise, we go back to that connection. And that connection will only come back when the channel is there. So that is basically our safeguard for the channel as well. So we unwrap it here, assuming that it's there. If it's not, it will just continue to loop. So that's kind of the way that we cover our errors is there. And then we bind to the system monitor exchange. So this one needs to exist before. So you need to create it manually. And we don't have a routing key. We want to route it to everything. And then we just call the publish message on that queue where we publish our whole message. And we wait and we unwrap, because basically that should work because we have everything in place. Again, you can also do that with that while loop here. But I think that this already gives a great idea how to do that. Better than the documentation examples, because they suck. All right, so that is the server. Let's run that server. Cargo run. It's running in the background. And let's see what happens if we kill the server. We should see a reconnect. And this is something that often is overlooked, weirdly enough, that people do not actually test their reconnect loop. And yeah, sooner or later that server will go down and you need that reconnect loop there. So let's stop it. Let's put in my password. I need shorter passwords. There we go. See, trying to connect after error. So the server detects an error, and if we start it, it should go back into operational mode. There we go. And is it doing it? Is it doing it? Of course it is. There we go. It started, boop, and it's open again. So the server is working. Okay, let's have a look at the client code. So let's go to the consumer, and the consumer is always more complex than the server in message queues. So we have this main, and again, with the same connection details, we have a consumer with crepes, and my guest has the password herpes. So if you ever want to log into my guest on my demo system, which you can't be because it's only running locally, and I create a Tokyo task that calls the function system info with the connection details, and this does all the heavy lifting. And we just await it, and this will await until we actually stop the consumer. So this is that system info. And first we're going to create a nice unique queue name. And we need to create that as arguments that we pass in later on. So I create a UUID, I create a queue prefix, C for consumer, then the exchange, and then that UUID. And that way we have a unique name per consumer, which is very useful. And I can see immediately, oh, this is a consumer and it's bound to that exchange. That really makes it easy for administrative tasks. And here we create the basic consume arguments that we need to pass later on over there to actually satisfy binding it. Then, well, we set up that connection and the channel, the same as we did with the server. It's the exact same functions. You should actually put them in the library. I didn't do that for documentation purposes. If people just want to see a client, then can easily look in here. I assume that you're clever enough, like, we're going to reuse that. Let's create a library for that. And this is where some magic happens. This is my bind queue to exchange. And I do a bit more, something that I did not discuss in the installation. I created a exchange for dead letters. And what is a dead letter? As soon as you not acknowledge a message, it will be automatically routed into a dead letter exchange that we created manually. So let's show you. Here we have that queue all.deadletter. And in each of our queues, this is what we actually are doing. We set this property x deadletter exchange, and we point that to all.deadletter. So we get the dead letters, so the messages that we do not acknowledge in this queue. So here we see we currently have 127. And there we go, 128. So we receive the dead letters that we do not acknowledge for whatever reason. And that's, I think, a good habit. And I urge you to actually use these dead letters and always acknowledge and not acknowledge messages yourself, not just rely on the auto. And in this case, we simulate this here, that every 10th message we do not acknowledge, so we can actually test that dead letter queue. And that is very viable information, because if for some reason a message couldn't be processed, it is nice to actually have the original message as well. But your applications should log sensible messages as well. So, but better safe than sorry. Right, so here when we do the bind queue to exchange, we actually check again whether that connection and the channel is open, just the same. And then we create a queue parameters that will actually set the whole parameters for the queue that we're actually going to declare later on here. So we have the queue name. We have auto delete set to true. Actually, I was doing a little experimentation before. This is how it is really in the queue. So auto delete, in this case, as soon as the client is gone, you delete the queue. And since you delete the queue anyways, then in that case, the messages don't need to be durable. In certain cases, you want to have a client use its own specific queue always and have the messages be durable. For example, a trading system. In this case, we're doing system events. Well, that data is still by the time you come back. And needless to say, in that case, you will not create a dynamic queue name, or you create it and always bind to that. But that seems to be logical, right? I hope. And then we just bind everything. And we have a nice queue set up bound to the channel. And we consume it only when the channel is there. So we bind that queue to this system monitor channel, which is also created already by hand. You need to create that. So when that queue is there, we have a channel, we bind to that. And that is basically how we go about setting it up. And then we go into our consumer loop. So we get messages and we await them, and every time this closure is called. So for each message, we just unwrap it. We can safely unwrap it, otherwise it's not called. And we convert it to a lossy format, a string, which in this case is perfectly fine because we're using JSON. And we print it to the screen. And like I said, every 10th message we do not acknowledge. So we can test that dead letter queue. And this is how you need to set up all the arguments, which is a bit tedious, I think. They should have abstracted that away a bit nicer, to be honest. But yeah, it is what it is. And for the other message, we just acknowledge. Well, we have that counter that counts. And that really is it. And otherwise, we throw an error. And then it will go back into this, this loop again to reconnect and set everything up. And this is how we survive server reboots and weird things. Okay, let's do a demo. Let's first start the system info server or publisher. All right. And then let's start a client. And that client will create a queue dynamically and bind it to that already present system monitor exchange. And there you go. It's already consuming it. Now let's log in. And there's an important thing. A guest user has the password guest at default. But you're not allowed to publish using the guest username from a different host. Hence, I use that consumer username in the client. And of course, always change your passwords. My guest has herpes and my consumer has grubs. And there you go. We have a nice little publishing going on. Let's go to the queues. Here is our queue dynamically created. And let's start a new client. This would be, for example, on a different host or a different Kubernetes instance. Boom, enter. And we should, yeah, there it is. It pops up. And let's do another one. And this is the power of fanout. It just publishes it once and the whole RabbitMQ does the heavy lifting. Look at that. We have a lot of different consumers consuming a single message. Although, if that is your question, yes, this message is actually copied to different queues for real, physically on the queue. So it's not that one instance is kept around and only when everybody acknowledges it that it is deleted. It's actually duplication in the depths of RabbitMQ. So yeah, look at that. This works nicely. So we have that system monitor exchange and all the bindings that are done automatically by the client. This works very, very nicely. And all those queues that are dynamically created and consumed. That looks awesome. This, by the way, is before I added the dead letter queue. That was more of a last minute idea, but I can guarantee you that works. So now let's see if we can actually stop this and what will happen. So what will happen? Let's create a new tab so we can actually stop the server. System control stop RabbitMQ. I should have created an alias. It's a lot of editing. There we go. My enormous password. That's the way how I call my thing. It's an enormous password. Yes. Okay. Stopping it. And also this is not one of the fastest hosts. It's a laptop which is 5 years old. And there you go. Yeah, we see that the server and the clients notice that there is an error. And it goes into that reconnect loop. And that is exactly what you want. And let's, yeah, every one of them is nicely acknowledging that the server is not there. And even the web interface isn't there. So we actually know that we're not cheating anything. Let's start it again and it should recover. Start, there we go. And like I said, this is an old laptop and it really performs nicely. There you go, everything just reset and everything is working again. The publisher / the server and the consumer / the client. Here you see the server just like, okay, I'm working again. So yeah, we have created a nice little recoverable set of RabbitMQ publisher and client. Now let's have a look at the resident memory of the publisher. Let's see, grab system info. And that is only 19 megabytes. With Node.js, you have a lot more of memory consumption for one of these processes. So there you have it. We created a publisher and a consumer in Rust for RabbitMQ that survives a server reboot. Now you can add some more error checking, for example, if an exchange exists or a channel exists. We did not really explicitly implement that, but that is now up to you. And I think you can do that easily because we have that restart loop, so it's just basically putting it in there. And RabbitMQ is a really great solution, so I suggest using it, especially when you're orchestrating between different services. Having the responses travel over a message bus is far more reliable and often also a lot quicker. Now the big question is, when do you use MQTT for Internet of Things or RabbitMQ? That really depends on the size of your applications. MQTT is a great message bus. We used it in the past on this channel and it's really nice and small. It's not as feature rich as RabbitMQ. You don't really have to fan out things that does it automatically, etc. So yeah, that's basically the trade-off. If it is just a one-to-one, a direct queue as RabbitMQ uses it, Mosquito MQTT works just fine as well. So those are a couple of things to keep in mind, and I hope you learned something and see you in the next one. I'm going to watch a few rabbits shag. Rabbit porn, baby, rabbit porn.